let's talk about motors as a whole. Now, the motor system has three elements. It has a power supply that goes into the motor. The motor itself has to do something with that energy that's being given to it. But how much energy the motor has on its output is determined by the load. So one of the things that is very important is to look at all of these three parameters. If we only look at one of these parameters, such as the motor, we could walk away from the motor and it could fail within 5 minutes of us walking away thinking that it was in good condition. And that's the problem. With condition monitoring, we have to look at all of the aspects that could lead to an electric motor failure. And there are many, many aspects. But like I just said, what is effective, what's practical, and what's economic? This is the doubt that I've come across in the marketplace. And to be honest, salespeople such as myself can often kind of convolute and add a bit of complexity to the situation for our own selfish needs, to be honest. But to look at the test equipment that we have, a lot of the equipment that we have is aimed to be very effective and functional in the right direction. I'll be honest, we do have some features in our test equipment that aren't going to deliver huge savings. So we probably wouldn't push those aspects as much as we would some of the more effective ones. So let's talk about the different areas that we can test motors, and you know, where the different tests would be applicable and the different applications that they would be applicable in, because different motors need different types of test. An electric motor most commonly is the picture that you can see at the bottom there. It's an induction motor. It's a very common mass-produced unit. But like the top one, a slip ring motor that is usually on high loads, these type of motors aren't typical, aren't easily to get hold of. So we also need to know how to test them best. I mean, this one, for example, has windings on the rotor, whereas the bottom one has no windings. It's just a solid core. So different motors have different characteristics that we need to be able to apply the right test to. So what is the motor? The purpose of a motor is to turn electrical energy into mechanical energy. It's as simple as that. You know, we could overcomplicate it with flux and words like that, but let's keep it simple. And yeah, we put power, we create a magnetic field. The magnetic field rotates. The rotor becomes a magnet to that rotating magnetic field in the stator or the field frame, and it just follows it. It just tries to keep up with that rotating field all the time. So that's it really. It's as simple as that. So, but what we also have to take into consider is the power supply. How much voltage do we put into that motor? And the purpose of it is to provide the motor with electrical power with voltage and frequency that are specific to be as economical as possible to the design of the motor. Now, power supplies can be fixed and variable. We can have VFDs, we can have soft starters. I think the picture there is an actual soft starter. So there are various different control circuits that can affect our motor as well. So we also have to be monitoring the power supply. And the power supply could also have issues. It could have high resistance joints. It could have contactors that are burning out. All of these different things need to be taken into account. Otherwise, a burnt out contactor with a high resistance joint might put higher current on one phase than the others, for example. So therefore, the motor's seeing that high current. A VFD may create distortion on the circuit, and it may even create distortion of enough that it wouldn't just affect the motor that it's driving. It might affect all motors that are on that bus bar. So there are several different applications of panels for different types of motor control circuits that we need to look at and understand. And then finally, the load. The load is also very important. If you can imagine driving an electric motor with a good power supply, a good motor condition, but the belt is slipping. So if the belt is slipping, every rotation it slips a bit. So if you can imagine driving your car, dabbing your foot on the accelerator, basically that's what's happening every time the belt slips. So you can imagine, you know, the longevity and the condition of your engine is going to deteriorate fairly quickly if you're dabbing your foot on the accelerator instead of operating it in a nice, smooth, speed up and slow down way. So also, you know, as simple as a belt, let alone problems with, you know, cavitation from pumps or gearboxes with you know, contamination issues and you know, crushers and mills, etc. Lots of different applications with motors that have unique issues on torque that can lead to the load having a big effect on the longevity of the motor, leading to failure and overload as well in certain situations. So there are three definite areas that we need to monitor. So why do we do it? Why do we test and monitor? Well, let's look at some information here. Probability of failure. Well, when we have a new application, there is always a degree of mortality and fatality. And this is because a lot of the time applications are not always suited, or there's been an issue with perhaps the new motor has been connected wrong. Perhaps the new motor isn't quite rated correctly for the application, etc., etc. There are lots of infant mortalities with electric motors, especially on startup. Startup is the worst condition that a motor will ever face during its operation. If you can think, an electric motor's full load current might be 100 amps. So that is when it's fully loaded. But during startup, it could take 8 times that current. So this is why if there's any weakness in the motor, you know, the spikes of voltage and current during that startup are likely to initiate any failure mechanisms within the motor itself. But we should then settle down to the useful life period. You know, on an electric motor these days, if it's got a good supply, the load is well within its acceptable parameters, and we look after it. We grease the bearings. We make sure that it's in, you know, cared for as much as it possibly can be. Then this motor could last 20, 30 years. So it's not a short-term issue with electric motors. You know, we're looking at long longevity, but also a lot of cost. If they fail without giving us any warnings and unexpectedly, then the downtime and lost production can be huge for some customers. And then end of life. When things do becoming, the bearings in particular, only have a life expectancy of so many years. When they start to deteriorate, they'll start to wear, pick up debris from within the bearing itself, and start affecting the races, which starts a downward spiral and increases the failure rate very quickly. Same with the electrical aspect. People often think that the windings they don't move, they're varnished, there shouldn't be an issue of deterioration. Well, that's not quite correct. If you look at a slow camera, for example, of a motor starting up, even though the windings are braced and have strapping and are varnished, you can still see that the varnishes in slow speed photography bounce and move, and when they're heating up and cooling down, of course they're expanding, which creates the physical effect of all of the vibration between the turns and the coils of the motor start to rub together, and the insulation between the coils and turns of the motor is very thin, and this can lead to the insulation becoming that thin that during the next startup, perhaps the insulation isn't as strong to take 8 times the current or a spike of voltage. Perhaps it will start to short and arc inside, leading to the failure of the electrical side. And I've already spoken about the bearing. You know, the bearing can gradually deteriorate, start to pick up a bit of debris, and then that debris accentuates more wear and the fast demise of the bearing. So there are lots of technologies, mostly associated with condition monitoring of electric motors. It is basically vibration. A lot of customers I speak to say, yeah, we do condition monitoring, we do vibration analysis to our motors. Okay, so that takes care of the bearing and maybe a little bit of the load issues, but what about the deterioration of the windings? How is vibration going to monitor that? Well, of course it can't. We have to use other things. Oil analysis is also often used for bearings that are on big motors. So sometimes they don't actually have rolling element. They might have just a sheath that is filled with oil, and once the oil starts spinning on the rotor then coats itself with the oil and basically it spins within the oil itself. Thermography is another one. A lot of people also say to me, yep, we got the mechanical side covered with vibration and we got the thermography covering the electrical side. Well, again, a lot of the things that thermography can find are, if we look at the motor frame itself, we can only pick up surface temperature. So the surface temperature of the motor, okay, we've gone along and we've found it's hot, but something's gone wrong internally to that motor for it to create heat within the motor itself, or there's something wrong with the load. So thermography kind of tells us not early on in the process that there's a problem. It kind of vindicates that, yes, we've got a problem. Same with vibration. Vibration often doesn't pick up the root cause, but leads to a subsequent mechanical reaction to that root cause. And then finally, electrical testing. Now, there are two types of electrical testing we can do. Unfortunately, there is still no technology viable at the moment that allows us to test insulation systems while the unit is energized. So we have two aspects. We test the motors when they're static, when they're switched off, and we look at insulation resistance, for an example, making sure that the motor is safe and within international standards of acceptability. Then we look at the dynamic. What does it do when it's in rotation? Well, how is the motor performing? So when we look at dynamic testing, we're in particular looking at the how the motor is reacting, one, to the load, and two, to the power supply that's put into it. So there are many aspects to dynamic testing that can lead to failures. Like I mentioned earlier, we could have distortion on the power supply, or we could have a slipping belt. Now, we can detect slipping belt very easily by just putting a current clamp and a voltage clip on the MCC. Perhaps the motor itself is in an area where we can't see that the belt is slipping. We can't even hear it. It's in a noisy environment, but we would be able to see it by looking at the torque frequency. So if we were monitoring torque on the dynamic, we could see that the belt was slipping, because every time the belt slipped, suddenly the torque would drop, and then it would come back again as soon as the belt took grip. So we would see through just monitoring the torque from the panel, through looking at the electrical parameters, we can calculate torque very accurately, and we can plot it. So this is a really good aspect of monitoring the mechanical side, sometimes when we can't even get vibration analysis and sensors to the unit. So when we look at ultrasonics as another device, this is listening to the sounds of failures and vibration, monitoring for excessive mechanical movement and displacement. Thermography, we're looking at temperature increases or decreases, and then of course audible. But all of these, as you can see on the orange curve there, are the path for a failure due to its earliest possible time. But if we applied simple condition monitoring techniques, that we found that the bearing was starting to fail, or we found that that we had a loose connection through time-based monitoring, we would be able to say head off a lot of these issues and maybe even eradicate them altogether. and keep the motor and the plant running with minimal downtime. And with condition monitoring, of course, we're able to plan that at the best possible time. So maybe even not even have an unscheduled outage. You know, we could schedule that maintenance at a time when the unit has to be cleaned for its production purposes, etc., etc. So there are many applications where you know, electric motors maintenance can be slotted in to avoid any costs to manufacturing process. Here's a few pictures of different things. That's me up on the left. That's an actual wind turbine generator. I was doing vibration analysis. You can see the silver probe on the side there. We were looking for issues with wind turbines. There was a lot of bearing failures, and this particular customer was very concerned after buying the wind turbines from a supplier that he wanted an independent view of the mechanical strength of the wind turbines before they paid their final bill. So this was like a quality assurance visit, just to double check that you know, the generators were working well in the applications and on the site that they were designed to do. We have oil analysis on the right. You know, this is a prime example of a bearing housing. We take a little bit of oil out and we look for particles within it. Now, as the bearing breaks down, it will give off zinc and a few other metals that go together to put in that an electric motor bearing is made of, and enables us to determine whether the breakdown is occurring. Particularly in noisy plant, a lot of people use ultrasonics, and you can see the guy down there, he's pointing, looking for air leaks on a pneumatic panel. But we can also do the same with arcing in panels and things like that. So ultrasonics does have its place, but also it's kind of, the damage is already starting to happen and the problems are already occurring when we get to detect any of these. Same with the thermography. You know, we're already starting to see the motor starting to overheat by the time we react to it. So there are a lot of different tests that we can do in condition monitoring, and this is just a fraction. But a lot of the time, we really want to do predictive maintenance and proactive maintenance to avoid the failures in the first place, or at least to give us an opportunity to correct any deterioration before it becomes a major issue that could lead to one of these other elements start to over-vibrate, start to overheat, start to deteriorate mechanically, etc. And if we look at motor problems, just to give you an idea, mechanical on low voltage motors is by far the most common. But when they do have issues, we can pick up things like heat, vibration, noise, that will enable us to determine what the issue is, like I said, through the tests that we can apply. But basically, when we look at electrical tests, often there is no warning that the insulation is getting to the point where it's going to fail. It's just that next time it starts, that spike of energy, the spike of voltage, when the contactors come in and they, just before they make contact, it gets to a very close distance from making contact, and there's a spike of energy, an arc, and that arc would be many times the actual voltage being supplied. So we have a high electrical spike, we have a high current spike due to the motor trying to start. So volts times amps is power. So if you can imagine, the power in the startup going through that motor is the worst conditioning we'll ever see. So if there are any weaknesses, that's when we'll find them. Here's another couple of studies, and again, once again, you can see that bearings are most common, but like I said, they don't generally fail without any warning. So if we're doing the right tests, then we often can pick up something, get some grease in them, and continue to operate. But the electrical and the rotor, etc., they're the ones that we need to be monitoring for, because when they break down, we get no warning. Here's another study. This was by GE. This is their numbers that they come up with. But as you can see, once you start looking at larger motors, it's not the bearings that are at failure anymore. Now the roller bearings are only 12% instead of 50%. So the electrical side becomes more prevalent. And when we get to the larger motors, this often means that these are more critical motors in our plant. Nobody has idle $100,000 motors sitting idly in their plant without any good reason. So usually these are a critical role to the manufacturing or whatever the plant or the plant or the company, the firm is wants to do with that. So when it's that critical, we don't want it breaking down unexpectedly. So if the majority of failures on motors 4 kV above are electrical, then perhaps we should make sure that we're doing electrical tests, not just looking at vibration testing, for example. So here is a chart of all the different things that can go wrong with electric motors. I'm sure there's probably one or two that are not missed, that are missed there. But when we actually look at what we can do to stop these failures from happening, how do we determine before it gets to a failure the type of testing or the type of condition monitoring we can do to identify the area before breakdown? And when you actually look at it, there's only 6 options. There's testing, online testing, so static and dynamic testing. There's infrared scanning, temperature trending, vibration analysis, visual inspection even, a simple one, and oil analysis. You know, all of these areas that we've identified there can be indicated through these simple condition monitoring tests that are all fairly easy, reasonably cheap to be able to maintain for any maintenance team. So, like I said, here's a more modern one. It's another IEEE study, but you know, the number 2 cause is electrical failure, and this is the one that doesn't give us any warning. So this is the one that costs businesses the most money from surveys that have been carried out. So why does insulation fail inside an electric motor? Well, there are many reasons. Thermal aging. You know, the hotter the motor works, the faster the deterioration of the insulation, and there's an IEEE standard that comes up with that ratio. But really, you know, when we look at power supply into an electric motor, for example, if we're not putting exactly the right voltages and the currents, and the frequency into the motor, and we're not looking after the load, then we're asking the windings of the motor to do a little bit more work. So therefore, the internal temperature of the motor is going to be a little bit higher. So therefore, the hotter environment of work that the motor works in, the faster the deterioration of the insulation. It's as simple as that. Contamination. Now, once we've got this hot temperature going on inside the motor and the decreased insulation condition over a period of time, what can speed that up is chemical deposits, you know, abrasive sand and dust that does seem to get into electric motors, especially in industries such as mining, etc. So we have to service these motors on a regular basis and make sure that we're keeping the seals on the you know, any guarding, etc., from trying to create a best environment we possibly can for the motor. Moisture is another one. A lot of the time in hot environments, in particular in Asia, we do see a lot of condensation building up in the electric motor. So we need to be careful of all of these areas and make sure that we're doing our best to determine how to manage those. Mechanical movement, you know, the more, let's just say we're driving a fan that's a little bit unbalanced, then the motor is not only heating up and cooling down internally because of the windings and moving around because of the startup, etc., but also it's vibrating. So there are, you know, each one of these little areas just adds a little bit more of negative environmental impact to the motor, which leads to, you know, the longevity of the motor deteriorating. Over voltage spikes. Now what we mean by that is, again, if we're switching the motor on and off on a regular basis, now sometimes we can't help it. An application, for example, a compressor is often the case that we have a situation where the compressor would just naturally builds the tank of air pressure up, and then during that air pressure the compressor is used, so therefore the tank drops down, therefore it will start the compressor up, it'll have a spike of energy, it will fill the tank up, and then the motor will switch off. And then as the air gets used again, it will drop down to a certain pressure, the motor will start again. And the more the air is used, obviously the more the motor is going to start and stop. And often with compressors, there's a high level of torque. And so the motor in particular on a compressor is exposed to high startup currents, and is quite a nasty environment for an electric motor. So we have to mitigate that by doing the best we can and make sure that we're doing, trying to avoid these over voltage spikes from creating this potential arcing inside the motor. And VFD drive, VFD I find is an easy way to explain it is a bicycle. If we're riding our bicycle and we want to change gear, what you find is as the gear is changing, we start to freewheel a bit, and then when the next gear kicks in, suddenly we have a little bit of a spike of energy that we have to push through the pedal to get it going again and to get that pressure on the pedal. It's the same with electric motor. So every time there's changes, there's kind of that extra little bit of pressure would lead to a spike of voltage being called to help the motor, which again goes through the windings and can lead to surges, etc., that can lead to the arcing within the turns and the coils, which can carbonize and lead to shorting within the motor frame. Factors leading to insulation failure, load-related issues, overloading. I've come across several mixers in my time that people are supposed to start them clear and then add whatever they want to mix or grind. Well, often people are a little bit lazy and they leave product in there and try to start the motor on under while it's trying to mix and cut whatever it's doing. Same with a pump. Often there are dampers and damping valves that open and allow the flow, etc. Same with fans, and quite a lot of different applications. So we need, again, to make sure that the motor is having the nicest time it can. It might mean that we have a soft starter. It might mean that we have various other starting techniques, such as a fluid coupling, which is mechanically way of being a soft start. All of these things will help the motor to avoid having these spikes of energy going through particularly the starting and stopping of the motor. Power quality, particularly distortion, can lead to overheating. Distortion is often associated with VFDs. A VFD would take a AC waveform, it would chop it up into DC pulses and supply that to the motor. So the motor will be seeing pulses instead of a nice smooth AC waveform. And often an electric motor will react noisily. And sometimes if you've ever had the opportunity to stand next to a motor starting under a VFD drive at a very slow speed and gradually building up, you can hear the motor subjected to some very strange noises as it's going through its speed range. And this is because of the distortion and the voltage that's being applied through the motor. Discharges and corona, partial discharges can happen when the deterioration of the insulation gets to a point. Also voids in the insulation often lead to discharges, but once the voids are there, there's not a lot we can do about them other than monitor over a period of time for deterioration. Startup and shutdown, once again, voltage spikes, starts. It's much better to leave an electric motor running. And I often get asked if I've found a problem with an electric motor. They say, well, we can't get it out until 6 weeks time. What can we do to help us avoid the failure until we get an opportunity to work on it? And my advice is always the same. Well, once it starts, leave it running. The more it starts and stops, so if you're going home in the evening after the afternoon shift and switching it off before the early morning shift come in, maybe just leave it running if it's that important to you. Okay, it's going to cost you more energy, but at the same time, it's probably going to be able to continue to operate. Little things like that. So when we look at an insulation curve, here we have two examples. Now, the insulation strength at the top here in an electric motor, is usually a thick piece of plasticky, Nomex style insulation that fits in the slot that the winding will actually sit in. And it's, like I said, it's mechanically thick and strong, and often rated at 28,000 volts strength, dielectric strength. But what happens over a period of time and years, that insulation will break down. And when it breaks down to the point of the supply voltage or the bus voltage, that's when the motor will become shorting within the turns. And the reason for that is electricity wants to get from point A to point B as fast as it can. So instead of going around all the turns in the motor, if it can jump over some of those turns to get to its circuit end as fast as possible, it will do it. So what will happen is internally to the motor, you'll start to have arcing across until it becomes a hard short, fully carbonized inside, and the full flow of the current will be missing out the turns. And then at that point, the turns would become short. Because they're shorted, basically they're a closed loop. And the rest of the inductive circuit of the motor winding would heat those turns up to a point where they become red hot and totally burn out. And this will all happen within a few seconds or minutes of that final startup and that final arc that had created the short, and the motor insulation strength to deteriorate to the line voltage value. And this is the root cause of why most motors fail in the field. Of course, when we go up to test the motor, we might find that it's blown to earth, or the insulation resistance is 0 to ground. But the root cause is the winding deterioration, because this is the weakest insulation in an electric motor. So anyway, here we have motor B. And if we look at the time here, the time is much less on motor B than motor A. So motor A has lasted a lot longer for some reason. So what are the factors? So let's look at dynamic testing. So here's motor A, static testing. What will that tell me on this curve? Well, we test it periodically over time, and once we test the insulation at this high voltage, looking for the deterioration of the insulation condition in a controlled way, in line with IEEE, IEC, ESA, many other organizations. But once it gets down to that point, we can obviously say that the motor, we'll see that the motor has failed. So we have a couple of warning spots there, and we can say that, okay, on this date, we found that the insulation condition between the cores and windings was this strength, and then next time it deteriorated. So we can start to trend and predict where this failure is. And this last little bit here of the failure could take as little as 6 months, or it could take a year. So as long as we're doing testing on a periodic basis, which is what condition monitoring is all about, would enable us to come up with a plan to avoid breakdown and change that motor out, or service it, or whatever we needed to do in the most economic way possible. So dynamic testing basically tells us which curve we're on, what the performance of the motor is. Without going into all of the parameters, we're looking at the performance of the electric motor. So, complete system analysis. Yes, we cover power supply. Yes, we cover motor. Yes, we cover load. Dynamic electrical testing evaluates each component of the system and identifies the environment factors. Static evaluates the static integrity of the insulation weakness. So here's some practical examples. How practical is it in the field, condition monitoring? Well, if we look at the motor on the left there, you can see it's covered. To pull the guard off that, to test the motor at the terminals, even if it's if we're safe enough to do it, because there's a shaft next to it being driven by another electric motor that might be in operation when we wanted to test the one on the right. So, you know, it's not easy, and it would probably take 2 men, 4 men all day just to test one motor. Whereas at the top here, you can see myself with a client at a steel mill, and I've tested 8 or 10 motors in a row there in a space of about 10 minutes, 15 minutes each motor. And I've been able to determine that motor 1's good, motor 2's good, motor 3's good. Perhaps motor 4 is starting to show deterioration. Number 5, number 6, and number 7 are all good. So that means that this guy can now focus his maintenance resources at an applicable time to suit him, and in a way that will avoid catastrophe and breakdown for this unit. And this type of tester, by the way, is only looking at the motor winding condition. It does look at ground insulation, but it is mainly looking at the insulation between the coils and turns, which is electrically the biggest area of failure for electric motors. Up to 80% root cause is the winding insulation. And just very briefly, the reason for this is if you've ever seen winding wire on an electric motor, you'll know that there is a very thin layer of varnish on top of the windings of the copper conductor, which prevents the turns from touching each other. That is microns thick. It's very thin, and it does deteriorate with time, movement, and contamination. So this is what we're looking for, is to avoid that electrical failure as well as the mechanical failure, and loose connections, by the way, for thermography. This is a great panel for thermography. We could just look all around that panel looking for those loose connections and arcing that would start, particularly under the conditions with electric motors when they're being asked to start up and stop with all that extra power and spikes going through the motor. We mustn't forget about the motors in the stores. A lot of the time the stored motors are just important because we think they're in good condition, but they may have been there for years and years on end. And when I had my time in the motor repair industry, I often used to get panic phone calls from customers saying, oh, we sent the motor in for you to service and we thought we'd fit the spare. We came to start Monday morning and the motor's just failed. We haven't got any spares. We need it repaired as quickly as possible. And of course we would do that, but it could be avoided if they included the condition monitoring to the motors in their stores as well, not just the monitoring in the field. An important point. So how does condition monitoring save you time and money? Well, this is very common sense really, but I'll run through them quickly. So condition monitoring enables you to maximize capital investments with motor-driven systems. So how does it do that? Well, it preserves the health and extends the life of your assets. By detecting and notifying you, condition monitoring alerts enable you to proactively correct issues before they irreparably damage your rotating plant. By intervening only when the assets need maintenance, condition monitoring enables you to eliminate a lot of the preventive maintenance activities that aren't necessary or ineffective. You know, a lot of customers do time-based maintenance. So we'll repair that motor every 3 years, whether it needs it or not. But if it doesn't need it, and when I say repair, I mean it might just want cleaning and bearings replacing. But why would you do that if there's nothing wrong with it? You know, it's been proven many times over that condition monitoring leads us, and proactive maintenance makes us be smarter with our money. So instead of repairing something every 3 years, we could do this condition monitoring, and we could say, hey, this motor that's coming up for service, there's actually nothing wrong with it. But funny enough, the one that we replaced it with last year next door, that one's showing signs of deterioration. Perhaps we should look at that one again. And you develop a trust into these systems and understand the failure mechanisms by using predictive maintenance. It really has been proven to perform and increase reliability for plants. Make smarter asset decisions. Avoiding the premature replacement of healthy motors extends the capital investment. while maintaining high availability of reliability metrics, providing operations, maintenance, and engineering with visibility on how equipment is performing helps these teams make more collaborative and better informed decisions. The big one, insight into your asset's health enables proactive risk and economic-based asset management decisions about this type and timing of maintenance. By making these decisions proactively instead of in the heat of the moment enables us to eliminate catastrophic failures, but also making the most economic time of the conditions that we have. And as a result, you know, as you can see, it's up to 70% fewer defects this way. Extends maintenance staff's reach. Your staff focuses more on the motors when they need maintenance and can perform other tasks when they don't. In other words, rather than doing you know, time-based maintenance, going around, checking insulation resistance on other times than when we are conducting our condition monitoring routes, enables us to look at how much time we spend on different plants, areas of plant, and enables us to become more succinct and direct with enabling us to do them all at once in a controlled manner. So instead of picking a specific area and focusing on that and then going back to the area in 3 weeks' time and doing something next door, if we do it correctly, we can actually plan and be a lot more effective with our time and our guys' time. Reduces energy. This is a really big one. Electric motors are so often over-designed for what they are asked to do. When I visit many sites, I've found that we may have a 100 kilowatt motor, and the motor is driving a pump. It's driving the pump maximum, and it's only 60% loaded. Well, an electric motor doesn't really work in its effective, economic and efficient areas until it's 80% plus loaded, and that depends on the design of the motor. So, and it drops off pretty quickly. So if we're only using 60% of the load of that motor, then the efficiency drops down. So what we're really saying is that if that motor costs, I don't know, $50,000 in energy a year to run, then, you know, if we're supplying it in the wrong size motor for the wrong application, then that 50,000 may have jumped up to 60,000. So we should be looking at the electric motor, because there are some massive, you'll be absolutely amazed at the levels of money that can be saved with electric motors. Just one comment, 65% of all energy goes through electric motors in industry on average. So you think about it, everything that rotates and moves is usually driven by an electric motor. So making sure that we have electric motors that are working correctly in the right environment and the right rating for the application is also very important. So when we do dynamic monitoring and we're looking at the parameters and the performance, we can quickly tell whether the load is really reaching that area where the motor works in its most efficient zone. And some of them are shocking. You literally can cost yourself tens and $20,000 on one motor a year, and the cost to replace that motor with a more correctly sized motor could even be less with that. So the payback for that is within 1 year. And this is what dynamic testing enables you. If you use the right type of test equipment to identify that area, then we can actually put dollar values against each part of your plant to say, well, this motor is costing you 20 grand a year. This motor is costing you 30 grand a year. At that time, you probably don't know that. All that customers generally get is a bill, and on that bill will be the entire cost for the implant. It's very difficult for people to drill down to separate areas to work out what's efficient or not. And a lot of the time, perhaps this motor is touch and go whether it makes money, even if it was efficient. You know, if it was regrind, for example, in a plastics factory, I come across someone who I used to test their grinder motor regularly, and they said that through the study that I give them of how much money that costs a year to operate, they said they could, the benefits of the regrind that they were getting from the wasted product didn't warrant it. So they wasted all that time and all those years when they could have just carried on with the new plastic and not bothered about the regrind, which took away time, energy, etc., etc. So some really interesting case studies that we have to justify this type of testing. So in summary, what if you could prevent premature failures by identifying faults in advance? Well, you can, but you have to be doing the right tests. You can't just say that vibration testing is going to cover all, because it doesn't. This is from a selfish perspective, this is our Baker instruments that are designed specifically for testing electric motors. The two on the right are dynamic, looking at the performance. One is online testing. One is looking at the motor. We go up periodically to it and collect data as it's in operation. And then the same with the other two. One is computer-based, so we're enabled to trend, create reports for condition monitoring. And the other one is more of a workshop-based. So if I'm a rewinder, for example, and I've got a workshop where I want to test motors when they come in, and then I want to test them again when they go out, then we have a different unit for that. But really, these instruments are designed to monitor, measure, and report on the specific parameters that lead to the majority of electric motor failures. Now that's very important. A lot of equipment out there is general test equipment that looks at general parameters, but these are specifically tuned to look at the specific areas and measurements that would indicate very quickly early detection of failures or pending failures. Here's the last few. This was a nuclear power plant. This was a pump. They had 3 pumps in a row. Each pump was designed to pull 32,000 Newton meters of fluid through the pump. One pump was only pulling 28,000. Now the customer knew there was an issue, but because there's 3 pumps in a row that work together, they didn't know which one it was. And to pull one pump out was $180,000 because it was a very, very big pump. And if they had to do it unexpectedly, then it would create an outage for the power station, which would cost them hundreds of thousands of dollars. But they knew they had a problem, but they didn't know how to detect which one, because they knew the flow of the whole area wasn't up as much as it should be. So when they looked at the current across the 3 motors and they looked at their traditional ways of monitoring, the pumps were actually submersible pumps, so they couldn't actually get to the side of the pump. But you know, all the electrical parameters were there, and they couldn't find which one was at fault. So the decision was they were going to pull all 3 of these pumps out. However, we went along with our equipment and we said, let us test them. It was a new customer to us. He said, no problem. So we looked at the torque and we measured the torque on this particular pump. And as you can see, it's fairly stable on pumps 2 and 3. But when we looked at number 1, the torque was all over the place. So it was very erratic. And the customer then decided that, okay, we're not going to pull pump 2 and 3 out. We'll pull pump number 1 out. We'll continue to operate under less capability, but we'll investigate pump 1. And what they found was that when they pulled the pump out, they found that the bottom was actually missing. And what had happened was, in the pit, the ducting that kind of guided the water into the correct part of the pump to make it efficient and so it wouldn't cavitate, would actually corroded and dropped away. So they basically fished it out, fitted it, and got the pump back in working very, very quickly. It was a very easy fix. But without knowing this, they would have had an outage where they would have removed all 3 pumps and could have cost them a great deal of money. And you can see how big this particular pump is. You can see the guy stood there in the picture. So when it comes to electric condition monitoring of electric motors, we need to take into account several areas, but we mustn't forget the electrical side of the motor. This is an area that is so under tested in condition monitoring in the field, and this leads to the biggest area of downtime. And you know, it's not just a simple case of fixing the motor, reconnecting the leads, or anything like that. Usually when an electric motor fails, it fails to the point where it can be scrap. It can blow in such a way that it's damaged the core, etc. So, you know, we need to find these faults before they happen with electric motors. Okay, so that's the end of the presentation. I think we're going to go to some questions now. Let me pull the questions up. So let's have a look here. Okay, so at the moment there's no questions in the questions section. Let's have a look at the chat.
Thank you, Paul. We have one attendee raise his hand. Maybe let me unmute him to see if I have any questions.
Okay.
Hello, Andre. It's Andre. If you have questions, you can speak up because I've already unmuted you.
Okay, so there is.
How about this?
Yes, yes.
Is clear my voice?
Yes, we can hear you, yes.
Okay. Thank you, Paul. That's a good presentation. Thank you very much. I have two questions. One about to predict the lifetime. I believe that common questions come from management, you know, and I think it will be difficult answer to get great confidence level to determine it. However, I'm interested when you are talking about the dynamic testing will tell where the curve are we. But you know, in common application, there is no lifetime curve that's from manufacturer, for example. So how can we address this condition? I mean, how to compare the curve? That's first questions.
Okay. So
and then second question.
Okay, go on.
Okay. For the common failure mode, I think it's better to answer this. You go to the common failure mode slide next, and we have utilized MTSA, motor current signature analysis, about 2 years. But we have difficulties to make correlation between vibration phenomena and these tools. And we know that MTSA only attack for the rotor bar broken failure mode type. Did you have any advice on this?
Oh, yeah, very much so. I mean, there is the torque ripple, for example, like the case study that I just showed you. You know, that application in that case study was 100% real. The pump and the torque is particularly applicable in pump scenarios. By monitoring the torque levels, you can determine a lot, and sometimes you don't have to even look at the frequency to be able to identify the unbalance or you know, the bearing failure frequencies. But just looking at the torque against time. So if we're going along and we have a loose belt, for example, then as it slips, we have a torque issue. If we have a gearbox that has a problem, the torque's going to come along, and when when the mesh gets to the issue, then suddenly the torque's going to change, and then it will continue, then it will change, and it will change. And the same with the cavitation. Cavitation's a little bit different because it's erratic. There's no level, but it's such a messy sine wave with the torque. So torque does have its uses. However, it has its limitations. Vibration is definitely the best way to mechanically monitor electric motors, for example, because the probe can actually get right in line with the point of contact, which is the bearing. When we're monitoring torque, we're picking it up through an electrical calculation from current and voltage, but when we actually look at that, we've then got to determine the drive end bearing, the non-drive end bearing. If it's driving a pump, is there a bearing on the pump shaft, etc., etc. So there's lots of different frequencies there that we're not going to know and be able to identify very easily. We will be able to identify the motor bearings quite easily. But like I said, it comes with experience. It also comes with condition monitoring. If you're testing the same motor on a regular basis and you suddenly start to see, oh, the startup torque has increased, then is it has somebody tightened the belts? Has it decreased because the belts are stretching, so the torque is taking longer for the motor to start? There are so many applications for torque monitoring that would give us the indication that there's a mechanical issue. Is it perfect? Of course not. Motor current signature analysis is can only guide us, and then we have to use our own common sense. Well, not common sense, but our own knowledge of the application. Some motors naturally have high distortion through just a characteristic, whereas we might have an alarm through motor current signature analysis on distortion, in other words, power supply, on a VFD, and then the one next to it might be exactly the same, but that VFD is working fine. So then we can deduce, well, hang on a minute, why is that VFD giving us a poorer power supply to our motor than the one next door? Let's investigate, call up the manufacturer. Why would these be different, etc.? Well, it might be that the internal components to the RCDs, not the RCDs, the components within the VFD are starting to break down, so that it's not giving the motor the good supply that it should. So there are many applications and many examples, but that's my experience of using them and my knowledge. But I wouldn't, if you've got it, then it's something that takes a bit of time and a bit of effort to really get to know your plant, to be able to look at the minor details that can lead you to the right diagnosis of a potential problem.
Okay.
Sorry, it's a really, that question, I could sit for an hour on that question. It's quite a long one. Now, the curve, the failure curve, again, it comes down to the application. Every electric motor is, let's just say an electric motor is sitting on a shelf at a supplier's. Now that motor could be taken off that shelf, it could be put on a compressor. It could be taken off, it could be put on a pump. It could be taken off and put on many different applications. And each one of the loads has a huge impact on how that motor, the longevity of that motor in the environment that it's in. So when we're talking about, time in years, there are so many, I don't have a crystal ball. And it's only to be honest, it's only the people that haven't got much experience in should we say, maintaining electric motors really well, that can say that there's one rule for one and one rule for all. I mean, some organisations come up with a chart. Well, if this happens, it's going to fail on this date. But that, you don't know, because there are a lot of environmental conditions that can happen between there and then. I mean, somebody might you might switch it off one day, and it might be cold, so then when it starts up again, it might, the grease, for example, might be in a colder environment, might be more solid, whereas in in a warmer environment, it's going to be easier to operate. And just the grease is quite an interesting subject. And I used to work for a bearing manufacturer. I was always with Baker Instruments, and we're now part of the Megger organization. But before that, we were part of the SKF organization. And SKF is obviously the one of the biggest bearing companies in the world. So we had a lot of education time with vibration monitoring of bearings and various testing of bearings and lubrication. And one of the interesting things is that that I found in very broad terms, that grease inside a bearing is just, the grease itself is just a sponge agent for the oil. It's not until the motor gets up and running fast and is hot that the sponge agent releases the oil into the bearing, and the oil picks up the on the rolling element, the actual ball or the roller of the bearing, it coats itself in oil, and then from then on there's no metal to metal contact should in a perfect world happen inside the bearing. The other thing is with maintenance crews is a lot of the time the manufacturer has a bearing that comes with a certain grease. A lot of the time you go to a factory and they have a different grease, and some are compatible, some aren't. Some reacting against each other in a very bad way for the bearing. So the other thing to check is that you know, each time you get a motor back or a pump or a gearbox back from a service agent, that what have they put in it? You know, have we checked what grease that customer is using for his bearings, so that when we use our multi-purpose grease, then are we doing the right one? But multi-purpose grease is another issue. Let's just say we've got a vertical pump motor. Should we be using multi-purpose grease in a vertical motor? Of course not, because what happens is, you know, as the motor rotates, gravity and the viscosity of the grease becomes thin, that the grease, and when it becomes oil, just rolls out of the bearing. So we need to put in a particular grease that's got the viscosity that it's going to stay in place and is designed for vertical mounted rotating plant. So there are many different applicants, and I'm sorry, but there's no one simple answer for each of your questions. It's just a case of looking at the application, understanding it, and using your skills as a technical guide to try and identify the areas that we can improve the reliability of the plant, and use the correct tests to identify that.
Yep.
Okay.
Yes. Okay.
I did. Thanks for the question, by the way. Great questions, and I wish I had more time to answer them.
No. Yeah. Thank you for the answer. Paul, could you go to the failure mode slide? I will to screenshot on that slide.
Go to the slide. Okay.
Common failure mode.
Which one, sorry?
The title is common failure mode of the motor. Before this, this one. Yeah.
Yeah. Yep.
Okay.
What's your question?
So that's I would like to check the rotor failure mode. So there is no rotor failure mode.
Yep.
Damage the rotor bar, for example.
Damage rotor bar. So my background, like I said, was I worked for a large repair organisation in the UK when I first left school. I then immigrated to Australia, and I ended up managing another large repair shop before getting into instrumentation. Now, so I think it was 25 years experience of working in an electric motor shop. In 25 years, I came across broken rotor bars no more than probably 15 times in all those years of 100 motors a week. It's something that is talked about as being very, very common, and it's not. It's simply extremely rare. And there are only certain applications where I did come across it that were common. And what those applications were when a motor is started direct online under load. And what happens is you have a large motor that starts, let's just say, here's an example for you, a thruster on a ship. Now, a thruster on a ship is basically a motor that drives a propeller that moves the ship left and right. So it pushes it up against the dock, maybe. Well, those motors are always started under load. So if you can imagine starting up an electric motor, it starts slowly and gradually builds up its speed. But at that slow speed, the torque is really not very strong. So you can often, stop, the motor won't even turn. It will just sit there because it hasn't got the power to turn through normal startup. So how to get over that? They basically use a direct online method that puts so much power through the motor that it can, even at that startup environment, it will just force its way through its load. But the problem with that is the rotor becomes so hot, and because it's got all of that current shooting through the rotor, and then when it stops, because the motor is stopped but it's still under load, it stops with a jolt. It stops in very short time, and the inertia creates a lot of the issue. So what we've got is the rotor bars are subjected to massive heat very, very quickly, and massive start and stop inertia. And often than not, that leads to the cracks. But there's also, with modern electric motors, another key element here is that you can get a motor now up to 350 kilowatt that is an aluminium die-cast rotor. Rotor bars are a kind of an old-fashioned design. The majority of standard electric motors now, and when I say majority, I would say 90, 95%, 99%. And again, I used to get a lot of phone calls when I was in a workshop, and the customer would ring me up. He said, "We've got a vibration guy here that says we've got a broken rotor bar." I said, "Okay, we can inspect that for you. Send it in, and we'll." And the motor would turn up, and it would be a 30 kilowatt standard motor. And we all knew, because we were in the business type thing, that there is absolutely no way that motor would have a broken rotor bar, simply for the fact that it's an aluminium solid rotor, and that don't have rotor bars as such. And the good thing about aluminium is it's flexible. So even on high inertia motors, because of the flexibility of aluminium, rather than a brazed copper and brass bar going through the rotor, it's not subjected to that kind of inertia and failure. So it's much more controllable. However, having said that, if there is a damaged rotor bar, then there's two ways you can pick it up. There's actually three or four ways, but none of the offline way of testing for broken rotor bars is 100% conclusive. There are various ways that you can use inductance readings across the rotor. But what happens is, if you can imagine you've got a cracked rotor bar in a rotor, when it's rotating, if it's cracked, the centrifugal inertia will open that crack up. But then when the motor is stationary, that centrifugal inertia is closed back down. So often, statically, you can't even find it because it's not broken anymore. It's still making good contact. So static testing of rotor bars can be very difficult and unpredictable, and there's no conclusive way of finding out 100%, except for online monitoring. Now, when you do online monitoring, you can actually find indications that would lead to broken rotor bar, and there's an international standard that can lead to the broken rotor bar through motor current signature analysis. But you can also back that up by looking at the torque, because what a broken rotor bar does, every time it's cutting the flux, it's like under torque. So if you can imagine that as the rotor spins and it hits the magnetic flux of a certain phase when it's at its peak, as that rotor bar comes round, if it's open circuit, you've got no power. So the rotor will kind of drop. So if you looked very carefully at the torque output of the time waveform of torque, you would probably find a bigger ripple than you would if it was a good rotor. So two things with motor current signature analysis: check the torque ripple, and check that the rotor bar indicator is acceptable. That's what we recommend.
Okay, thank you very much, Paul.
No problem. Okay.
Paul, now I think we only have time to accept the last two questions. One is here in the question panel. During greasing, why the motor temperature will increase?
Okay, well, so I covered that a little bit earlier. When we put grease into a bearing, it takes a while for it to settle. You know, for the oil to be released from the sponging agent, perhaps before the motor has been in the bearing has been in a unlubricated state. Perhaps we've over lubricated it. It's hard to be predictable. I mean, theoretically, you know, you would think with the grease going into a bearing, it's going to create a harsher environment until it gets thrown out, and or the grease and the oil is released into the rolling elements. But that should happen fairly quickly, especially on fast-moving bearings. But the slower the bearing, you know, that shouldn't really happen. That shouldn't even happen that very long on those slow motors and slow bearings either. So I am interested in that question. Yes, initially it would go up, but my experience kind of leads me to think that when you give it an hour, then that should have settled down, unless of course it's overpacked, and then the grease is basically or the oil is almost cavitating within the bearing itself, so it's creating a friction because there's too much in there. But that's very rare. So yeah, I mean that's as much as I can say on that. What was the other question, Grace?
Thank you, Paul. We have one last attendee raise his hand. So let's see if he has any question for you. Riaz Abasi, I will now mute you. But due to the time limit, we can only accept one final question. Riaz Abasi? Hello?
Hello, Riaz, you're on mute at the moment.
Yes. Riaz? Hi, Riaz Abasi? It's okay. If you have any further questions, you can anytime email us. Thank you, Paul, today. Thank you for your presentation, and thank you for all your very good questions and answers from Paul. If you have any further questions, please email us. Recordings of this webinar and also certificates will be sent to you all in 2 days' time. And you'll also feel free to visit megger.com for any other upcoming webinars. And we hope to see you again soon. Thank you, Paul. Thank you, everyone.
Thank you, everybody. Bye-bye.
Thank you. Bye-bye.